Okay, so again, we are gluing this metric, Schwarzschild metric, outside of the body of the star. To the metric inside the body of the star, which is equal to d tau squared minus ia squared tau d chi squared sine squared chi d omega squared. And we have described this metric in the following sense that this a and tau as implicit as functions of parameter eta behave like this. Cosine of eta and tau of eta is a0 over 2 eta plus sine of eta, and eta is ranging from 0 to pi, and at eta equals to 0 the collapse begins. As eta reaches pi, the body of the star shrinks to 0 size. So now we want to glue this matrix to find the other parameters of the metric. So within this metric, the surface sigma, the surface of the star sigma, is just one of the surfaces inside the 3 sphere. So the one which corresponds to chi equals chi 0. So the metric on this surface is just ds minus squared. So it's a world surface in this case. The metric on this world surface is just d tau squared minus a squared of tau sine squared chi 0 d omega squared. So this is a metric on the surface sigma, restricted to the surface sigma. So just chi is fixed. At the same time, the metric on this surface sigma, from the point of view of this metric, is just ds plus squared sigma equals to 1 minus rg divided by r dt over d tau squared minus 1 divided by 1 minus rg over r dr over d tau squared times d tau squared minus r squared of tau d omega squared. To glue this metric to this one, to equate them, they should be equal because they are the same metric on the same surface. One is induced from this one, the other one induced from this one. To equate them, we have to have the following relation, that r of tau is equal to a of tau times sine chi 0. And 1, so this is just equates this to this. So basically this sets the radius. And 1 minus rg over r d tau dt over d tau squared minus 1 divided by 1 minus rg over r dr over d tau squared equals to 1. So these are the relations. Basically, knowing this, we know r of t. And knowing r of t from this equation, we can find t of tau. This way we will find world line of the world volume of the surface sigma. And well, this equation can be solved for t of tau. so t as a function of tau. So the solution is obvious. So t dot is equal to, well, for t dot can be solved, of course, is just square root of r dot squared plus 1 minus rg over r divided by 1 minus rg over r. And, well, again, t dot and r dot, this is just t dot, and this is just r dot. I hope it's obvious. So this equation, if we know r of tau from here, we can find t of tau after integration. Well, this is can be done, but let us just stress here that as r goes to rg, so as the surface of the star approaches its gravitational radius, we can asymptotically find the solution of this equation. So first of all, this term becomes approximately 0 and can be neglected with respect to this term because r as a function of proper time as follows from 0 is not 0, because a of tau as a function of proper time is not 0 in the vicinity of the horizon, so the surface goes with non-zero velocity. So we can neglect this in this limit, and this equation approximately acquires the following form. dt is equals approximately minus dr divided by 1 minus rg over r. Minus sign here appears because due to the fact that that dr is less than 0, because the surface of the star is shrinking as dt as the time goes by, as dt goes to future infinity. So this, due to this, we have minus sign here, and this can be solved approximately that r as a function of t is approximately equal to rg times 1 plus exponent of minus t divided by rg. So this is as t goes to infinity. As t goes to infinity, because as r goes to rg, as r big goes to rg, t goes to infinity. So we encounter the following situation, that despite the fact that it takes finite proper time for the star surface to cross the Schwarzschild radius, to cross the Schwarzschild horizon, so it takes finite amount of this for this to cross rg. But it takes infinite amount of time for outside, from the point of view of outside observer, for the star surface to cross the horizon. So star surface asymptotically slowing down and approaching the surface, the Schwarzschild radius. That is the situation we have encountered already for the particles in the lecture 6. So again, what we are doing, we are gluing this metric to this metric. Second derivative of this metric and this metric are related to the Ricci tensor and are fixed by Einstein equations of motion. It means that this second derivative of this metric is related to the energy momentum tensor in the corresponding part of the space-time. By gluing the metric itself, this and this, we were able to find A of tau through the parametric relation. From by solving Einstein equations here, we found this A of tau. By gluing this to this, from this we can find R of tau and T of tau. And we explicitly presented the solution for T of tau in the infinity as this time goes to infinity. So this is so far. What remains to be done is to glue first derivative of this metric to the first derivative of this metric. But it demands some differential geometry for the surfaces in space-times, which goes beyond the scope of our lectures. But the result of this gluing is pretty much obvious, and can be understood on general physical grounds. The result of that gluing just leads to the fact that Rg, this Rg standing here, is related to that what is standing there as follows: 2 kappa 4 pi over 3 r cube of tau times rho of tau, constant. Well, what happens is that why this is constant is because we have obtained that a cube of tau times rho of tau is constant. Well, what do we see here? That this quantity standing here remains constant, as it should be, as we explained on general grounds at the beginning of the lecture, and it's appropriately related to the mass of the ball, because this is the volume of the ball times its radius. And this is 2 kappa, as it should be. So, perfect. We have obtained the perfect relation between two metrics. Now we are ready to draw the Penrose-Carter diagram for this metric. So basically, what do we have here? We have the following situation. So outside of the sigma, this is what we call sigma of tau. So the surface of the sigma, sorry, not sigma of tau. So we have the following situation. We have outside of it, we basically have the same situation as in Schwarzschild space-time. So for the Schwarzschild metric, to remind you, we have there in Kruskal coordinates, we have there v and u. So we have this singularity, r equals to 0, this hyperbola corresponding to this singularity. And we have the surface sigma. So the surface sigma has the following. This is sigma. And it has the following behavior. Before t equals to 0. So this part is the same as we have encountered in the previous lecture for the star. And after t equals to 0, we have this collapse described by this situation. So this is sigma. This is sigma. So this metric is applicable here. In Kruskal coordinates, we have this. And in here, we have to glue what we have encountered in the previous lecture. And here, in this region, we have to glue Penrose diagram following from this metric in here. So, in here, from ds minus square, so to say. So let us draw what we obtained. Well, before drawing that, let us draw Penrose diagram for this guy. To do that, one can establish the following fact that a squared, this metric can be represented like this. Exactly with the same parameter eta as we have encountered before in this lecture. So this is compact because eta and kappa are ranging in compact regions. We can drop off this metric and consider this space-time itself, but we have to bear in mind that eta is ranging from 0 to pi, while chi is ranging from 0 to chi 0. Chi 0 is remember, the chi 0 defines us the surface of the star in this metric. As a result, this is just a part of the square, where this is corresponds to chi 0. In all, gluing this to what we, so before here, I mean here, in this region, we have what we have encountered in the previous lecture for the star. Here we have what we have for the same as for the Schwarzschild, for the black hole. And here we have this guy. In all, we obtain the following picture. The following Penrose diagram. Penrose diagram for this guy has the following form. So this is the region inside the star. This is sigma, the surface of the star. This is the moment t equals to 0. So below this region, we have the same Penrose diagram, which coincides with the same Penrose diagram as for the star. And this is r equals to rg, and this is r equals to 0. So this is singularity. This is scri plus, this is scri minus. So this is a Penrose diagram for the collapsing star, Perfect. Now, we see that for this case, we do not have white hole. We have a black hole. We have event horizon. We have the region here from which no one can escape to scri plus. So everyone finding himself here will inevitably end up at the singularity. But we are considering time-dependent solution. There is, of course, time reversal of this solution. Time reversal of this solution is given by a of eta equals to a0 over 2, 1 minus cosine of eta, and tau of eta equals to a0 over 2 eta minus sine eta. So we had a solution where there was a plus sign here, and now we have this solution with eta ranging from 0 to pi. So that solution with plus sign was describing the collapse. This solution is describing the reverse process. At eta equals to 0, we have 0 size of the ball, and it inflates, becomes bigger. And if at the moment eta equals to pi, something stops this inflation, and the radius remains fixed after that moment, for this solution, we obtain just a time reversal of this diagram, which is just a flip of this diagram over the horizontal line. So this is the situation we have predicted in the previous lectures, saying that for every solution of Einstein equations, we have its time reversal in case of if the solution is time dependent.